So we'll talk about state space analysis. And this approach is very powerful in its existence. And so far we have studied transfer function approach. Okay. So transfer function approach talks about uh, single input, single output system, or the systems where your initial condition are zero, right? So, or but transfer function approach is really good when it talks of when it comes to linear time invariant systems, and you have single input, single output system, so that you can represent it in the form of a fraction at initial condition zero, the Laplace of that fraction. So that way, transfer function approach is really good. But when we consider a bigger class of systems, when we consider not just linear systems, when we are trying to consider nonlinear systems also, and when we are thinking of time varying systems, so there is little bit of more complexity involved in your system representation, and you might have multiple inputs also. So your system is no more single input, single output. It is now multiple input, multiple output. That's we will call it MIMO, multiple input, multiple output system. So in those cases, we have a better approach, which is known as state space representation. So what is state space representation? State space representation for linear system is generally given by x dot is equals to a x plus pu, and y is equals to cx plus du. That's one of the most famous equation for state space representation of linear systems. And if we want to see the similar representation for nonlinear system, then we can just directly write it as x dot is equals to f of x comma u. So your x goes for the states and u goes for the inputs. So here also, this is your state matrix, and this is your state matrix. This is your input matrix, and this is your output matrix, and C is your output matrix, and D is your transmission matrix. Okay, so this is your output matrix, and D is your transmission matrix. So we generally represent uh, linear systems, nonlinear systems. In case of the nonlinear system, we don't have the clear representation of state space representation in the form of matrices, because you tend to not write matrices in case of nonlinear systems. You will have differential equation, nonlinear differential equations, and that's a good area of research to how to linearize the nonlinear system and then use the state space representation. That can also be done. And any kind of physical system, any kind of electrical, mechanical, chemical, or any kind of technical system can also be represented by state space analysis. So state space approach is very much wider if we think about it, and if we use it for our analysis of different types of control systems. So how do we see this approach in general by the small representation of pictorial representation? Then we can see, we can just have a look of the above equations which we have seen. We can draw a block diagram which represents the set of inputs. So it can be your U1, U2, U3, and UM. So that's your inputs to control system. Okay. and you have outputs from this system. Okay, so outputs can be your y1, y2, y3, y, yp, and in between you have the systems states, system states. So those are your x1, x2, x3. It goes till xn. So all of these three sets which I have made here will be the set of vectors. So this would be your input vector, and this would be your state vector. And so these will go and form the basically the column vectors. This will be a straight column vector, input vector, and output vector also a column vector. State vector will be a combination of many different state vectors. Okay, column vectors. So that will give you a state matrix, which we have seen here as A. Okay, so this A is a state matrix, and it's a combination of different column vectors. Okay, so that becomes that makes a size of n cross n when we represent it. So your A is a n cross n square matrix, and it is a state matrix. Okay, so your U would be an input matrix of m cross 1. Okay, your output matrix Y would be of order P P cross 1. Okay, and your D matrix, sorry, this output matrix is your C matrix. It is outputs are represented by, but your matrix is C matrix. So the dimension of C matrix is P cross N, and your dimension of D matrix, which is your transmission matrix, is of order P cross M. And by all these four different matrices, we can represent these two equations. In these two equations, one is your first order differential equation and other is your normal uh, y y is equals to cx plus du sort of equation. So all of these equations can be further written in the matrix form. But before that, if we want to see the little bit much more simplified version of this particular diagram, so we can write it as that's the U, which is this input vector, and that's your control system. I'm writing it as CS, and there you have output given by Y, and in between which represents the system, and that system is formed by the state variables, and which are your set of state variables in the form of capital X. Okay, so that's how we represent. This is the block diagram or pictorial representation of the simple approach of state space representation. So now if I would like to see how does it look in the form of equations. So the if I want to write the state equations, let me just write the state equations. I can write in the first order differential equation form, which is your dx1 by dt. And if I'm the linear representation I have given already, and if I'm talking of a generic representation, that can be your f1, x1, x2, x3. So it's an n vector, so it will go till xn, and then you have u1, u2. These are the inputs. You have an m order of inputs, so it will go till m. So then you have dx2 by dt is your x2 dot, and that's your function 2, x1, x2, x3 until xn. Then you have u1, u2, um, closed, and then similarly it will go till xn, and that's your x nth order differential equation, xn dot. This is f nth function of that particular differential equation and can be written in the similar fashion, and that's the inputs for the nth function. Okay. So that's the general representation of state equations in the form of first order differential equation, first order nonlinear differential equation. Now, this set of equation also represents the linear uh, differential equation, and as it is the generic version for the linear as well as nonlinear systems. And if I want to write it in the final fashion, then it would be capital X dot of t is equals to f of x of t u of t. So that's the state equation representation. Okay. And now we would like to see its matrix version, in the matrix form of the same above equation. If I want to write, then I can write it as x1 dot, x2 dot, x3 dot, then it goes on till xn dot. That's my one column vector is equals to then a11, a12, a13. It goes on till a1n, okay, and then a21, a22, a23, and then it goes till a2n. It can go on and on, and the final row of this state matrix, I can write it as A1, N1, AN2, AN2, and AN3. It goes on and on until ANN. So this sort of, you can figure it out that it's an n cross n matrix. It will be multiplied with the state, variable vector, which is x. Then you will multiply another B11, B12, it will go till B1M, as we know that this is an n cross m matrix, so its final element would be BNM, and it's your BN1, N1, BN2, it will go on and on and on. So that's the basic representation for input matrix B. Then you have U1, U2, and it will go till UM, as we know that it is the mth vector. Okay, so this is your general matrix form representation of the above equation, which is given in this form. So that's the representation in the matrix form. Similarly, you can have you can represent y is equals to cx plus du also. So there we will have the whole representation. So there you will have a vector of y. Okay, so y1 till yn. Then you will have a P cross n matrix. Okay, this will be P cross n matrix, which will be your transition matrix and a output matrix. So this will be your xn till xn state vector. Then you will have D matrix here, which will be your P cross M again. Okay, and then you will have a U matrix here again as M1 cross M vector. So I'm not writing the whole matrix here, but that's easy to write that. And this particular thing, this x dot is equals to fx is generalized version of the state space representation. And as we have seen that x dot is equals to ax plus bu is the uh, is the state space representation matrix. So we can also, write, we can make a block diagram representation of this thing, and that would be known as state model of the system. Okay, so if I want to write the state model of the system, then I can do so by making a block diagram which will have the input u. So we know that let me first write the equation, so it will be easy to figure out how do we write block diagram. So it's x dot is equals to ax plus bu, and y is equals to cx plus du. So this is the set of equations, and this set of equation should be represented by the block diagram. So what I should have? So u is getting multiplied with b and d. That I know. Okay, so that's my input. I know u is my input. Okay, so I can keep b as a multiplication here, and also d as a multiplication here in the block. Okay, so b and d are ready. Okay, then b and d both are getting added with ax and cx. Okay, so and I also know that so getting added, so there can be a summer, right? So this b goes into a summer positively, and what is getting added with b? Bu ax is getting added, and if x is getting added, then x has to be there, right? So if x dot is also in the equation. So if, for example, I have x dot here, so I would need an integrator to make it x. Okay, so I have that integrator here, and then I have x here. Now that x dot is equals to ax plus bu. So bu I have here, x dot is here. So if I add ax here, then this first equation is complete, right? So I'll add ax here in the feedback of this integrator, and this would take my uh, this kind of shape. Okay. So now if I look at this first equation, this is sorted. So x dot x is multiplied with ax, and then added with bu, and that is equals to x dot, and this loop is getting done. Now from here, this one equation is sorted, and then I also have the usage of x somewhere else. It is getting multiplied with c, so x will be getting multiplied with c here. Okay, and then it goes out, and as I know that cx is getting added with the du, so du I have here in the second part of this branch, which is coming out from the input side. So I'll add this here, and I'll add this here. Okay, so there would be a summer. Okay, adding two positive and giving me the output, and that output is nothing but y. So my output is here as y is equals to cx plus du. That's the block diagram model of I can say it as block diagram of state model of state model. Okay. I can also make the signal flow graph of this state model. As we know, we have studied it. So signal flow graph of this state model could be, uh, we know the nodes. We will see these points where, you know, there is something getting added or something taking off or something meeting. Okay, so we'll get the nodes, and so I have this node here. Then I can call it u. Then this is going with the gain b. Okay, and it's going to the node x. Okay, then it's going further So this is X dot here, and with an integrator, it's going at X. So this is another node here. Okay, further. And then again to C with the gain C, this is going to the node Y, which is the output. Now, if you see, notice this block diagram, A is taking off from X and reaching to X dot. Okay, so I'll make this branch with the gain A in the feedback. Okay, so it'll reach here, and again I'll uh, make another branch which will be of reverse direction than A. So it'll go from uh, wait, uh, it'll go from U to Y in the forward direction. Okay. So here in this way, I can make the signal flow graph of signal flow graph of the representation of state model. Okay, so that's my state model. Okay. So this is how we make the state model, state representation, and we can, as I have earlier talked that we can represent any kind of system in the way of this sort of matrix form or the generalized nonlinear form. So we can represent any kind of physical and technical system as a state space model. Okay, so we can represent any kind of system in the form of a state space model. So we will take some examples, and uh, we will see that how we are uh, considering different types of models for representation of state space model. So let's take one electrical network, and mm, it is one example which we are taking. Example one we are taking, and it's a circuit which has an inductor, and then another inductor, then another resistor, and then uh, one resistor at this branch, and then source voltage as E of t here, and it can be represented by R1 and L1. L1 is here, L2 is here, and capacitor I'm attaching it in between these two branches, which is C. Okay, and this is my figure 1. So now this is my circuit, and I want to represent this in in the form of a state space representation, and as a I want to write in equations and then represent those equations in the state space representation. So let's see how do we do that. And so we'll start with, first we will see what is which variable is changing with respect to time. If we write the equation for this particular circuit, and so I forgot the resistance 2 here. So we have two resistances, one capacitor, two inductors. So that's L1 and that's L2 here, and input voltage E of t, and that's my RLC circuit. So let assume the state variables first. So I can see that my current will be varying in with the inductor, with both the inductors, and there will be a variation with respect to time in the capacitor side. So first I'll use Kirchhoff's current law at this node, which I can call it as node A. Okay, and the direction of current I can make it like this. Okay. So if I am using the KCL in this figure, and I am writing the equation by using KCL, which can be I1 plus I2 plus the this side would be termed as C of dVc by dt. That's the current through this capacitor, and this is equal to 0. So by using the Kirchhoff's current law, I can write this equation. And by looking at this equation number 1, I can say that now I can think of the state variables. So what state variables I'll think? I can give I1 as state variable x1. So current I1 is my x1, and my x2 would be current I2, and this change of capacitor voltage will become my third state variable. So I would say that x3 is Vc. So change in Vc will be uh, differentiation of x3. So dVc by dt will become dx3 by dt, and that will become my first state variable in this particular equation 1. So if I want to write the equation 1 again in the form of state variables, then I can write it as I can write it as, I can, just a minute, I can write it as x1 plus x2 plus x3 dot. So x3 dot is nothing but C multiplied with x3 dot is equals to 0. So x3 dot is nothing but x3 dot is nothing but dVc by dt. So I have this equation, and from here I can just simplify it. I can write it as Cx3 dot is equals to minus of x1 minus of x2, and x3 equal to x3 dot equal to minus of 1 by C x1 minus of 1 by C x2. So that's my equation number 2, and this is my sort of, now I can see that equation 1 is first order differential equation, and now I would like to again have a look at this figure, and what I can do is now I can make uh, I can apply KVL in the two loops. I can see the two loops are there. So I'll try to apply the KVL in these two loops, and let's see what happens when we look at the first loop. So when we are looking at the first loop, we can see the figure in this fashion. There is an inductor, there is a capacitor, and the voltage across capacitor is Vc. So and then there is a resistance and the input source, which is input voltage is E of t, and the voltage across this resistance can be written as R1 I1, and I have the current which is passing through here is I1, so I can write it as L1 di1 by dt. Okay, so and Vc is the voltage across capacitor that I already know. So I'll use the KVL, and I will write the equation, voltage equation, that can be written as E of t plus R1 I1 plus L1 di1 by dt, and equal to V of C. So that's my first, I can write it as equation number 3. So that's my first KVL equation for the first loop. And as I know that I1 is my x1, I1 is my x1, and here we can see that di1 dt is there. So this will become as x1 dot, and VC is x3 already, we know that. And E of t is, as we can see, that it is acting as the source of for this particular circuit. So we know that it's acting as the input to this system. So E of t, we can write it as U. So overall, assuming these state variables and input variables and rewriting the equation number 3, and we can write it as U plus R1 X1 plus L1 X1 dot is equals to X3. And I can further write it as I have to write it as x1 dot equals to it. I have to make it as a first order differential equation. So that would be my L1 x1 dot equals to x3 minus R1 x1 minus U. Further going on, I can write it as x1 is equals to uh, minus of R1 by L1 x 1, and then my plus 1 by L1 x3, and minus 1 by L1 U. So that is my another state equation where I have a clear first order differential equation, and I am keeping it as number 4. So equation 4 is one differential equation, and equation 2 is another differential equation, and I have further one more loop in this particular circuit. So for that, I'll go and apply KVL again into this for obtaining the last first order differential equation, and for that I will look at the diagram and I can see this kind of situation with the inductor 2 and the resistance which is attached in the last branch. So that's my R2 I2, and this is the current going in this direction, which is I2. So this would become as L2 di2 di2 by dt, and this is VC voltage flowing in this direction. So uh, by again KVL, I can write the equations, and I can say I know that VC is my voltage across capacitors. So by applying KVL in this particular figure, I'll get the equation as VC is equals to L2 di2 by dt plus R2 I2. So that's my equation number 5. I know the state variables. VC is x3, and I2 is x2, and it's di2 by dt, so it will become x2 dot. And again, this would be my I2 is x2, so it will be x2. So I can rewrite the whole equation as x3 equals to L2 x2 dot, L2 x2 dot. It's a dot. It's a dot. Let me make a nice good dot. X2 dot plus x R2 x2, and I can further write it nicely as x2 dot equals to minus of R2 by L2 x2, and plus of 1 by L2 x3. So that becomes my equation number 3, which is a first order differential equation. So I'll name it as equation number 6, equation number 3 of the first order differential equation. So now I can combine equation 6 equation 4 and equation 2 together and write the final set of equations. So final set of equations is your x1 dot is equals to minus of r1 by l1 x1 plus 1 by l1 x3 minus 1 by l1 u, and then x2 dot here minus of r2 l2 x2 plus 1 by l2 x3, and then x3 dot here minus of 1 by c x1 minus of 1 by c x2. So this is the general state space representation in the form of x dot is equals to f of x comma u. So if you can notice here, this particular equation is nothing but the function of x and u. So it is the function of state variables and input variables. And similarly, you can also write the other two equations in this fashion. And these three equations are first order differential equations. So if I want to write it in very uh, nice matrix form, then I can do that in such a way. I can write it as x1 dot, x2 dot, x3 dot. This is my third order. This is becoming my third order system. So that's a vector of 3 cross 1, sorry, 1 cross 3 uh, column vector. Uh, and that's your one column vector. Mhm. And it will have three excuse me for this one, and it will have three rows here by r1, which can be written by r1 by l1, then 0, then 1 by l1, then we will have 0 here in the second row, then r2 by l2 here, and then 1 by l2 here, then 1 minus 1 by c minus 1 by c here, and 0 here, and x1 x2 x3 will be my state vector plus minus 1 by l1 0 0, and that's your input matrix multiplied with 1 u. And let us now choose the voltage across the resistances as output variables, and those output variables can be determined by your y1 is equals to I1 R1, and y2 equals to I2 R2. So your final output equation can be written as uh, your final output equation also in the matrix form can be written as y1 y2's matrix, and r1 0 0 r2, and that's your output matrix x x2 x1 x2. So now here in this way, we are able to write the state space representation for an electrical circuit. So your these two equations, which is marked in red boundaries, are the state space representation of the circuit, which was of the circuit which is shown here in the beginning of this particular uh, this is an electrical circuit, and by such a way we can represent an electrical network in the form of the state variables. And there is we can also take one more example where we can uh, think we can where we can see a mechanical system. and we can try to see the state space representation for that particular mechanical system. So let's take another example of a mechanical system. It's a spring mass damper system. Spring mass damper system. Okay. So the choice of state variables is crucial in these cases, and we just have to mindfully we have to think about the which will be state variables. So we can just think of those variables which are changing with respect to time. Okay. So for example, in the previous circuit, the current and voltage was changing. So I1, I2 can become two states, and the capacitor voltage VC can become another state. So here, what would be changing? Uh, we need to see that. So first, and what variable is changing, that we can identify when we write the differential equation first. So let's first have a look at the mechanical system, and then we will make the differential equations, first order differential equation for this particular mechanical system. So uh, this is the spring mass damper system, and this is the mass M1 of this particular setup, and we have a spring here, that's K1. There is a first damper, that's B1. Another damper is B2, and another spring is K2. And the force applied on this particular system is F. And because of the application of that force, there will be a displacement Y1, and there will be another displacement Y2. Okay. So this is how this particular mechanical system looks like. So for writing the differential equation for this particular mechanical system, we have studied already in the initial chapters of this course that how to write the differential equation for any particular mechanical system. We'll first make the free body diagram, and for that free body diagram, let's see how it will go. I'll first consider the mass M1, and the force applied on it is this. So the reaction force by the body itself will be going in the reverse direction, and it will contribute as m1 d square y1 by dt. In its differential equation, it will contribute this much, and then there is a spring attached. So with the spring, this spring is also attached to the mass m2, and when we are considering the mass m1, will go with the displacement, will give the priority to the displacement which is with respect to mass m1. So that is y1. So k and y1 minus y2 will be contributed by the spring towards as the reaction force um, for the mass m1 when the force ft is applied. And as we know, the force ft is applied, and the reaction force by the damper would be something b1. We know from the force voltage analogy, and from the force current analogy, and the analogy of electrical and mechanical system, that the damper will always come with the uh, velocity. Okay, so the first differentiation of displacement will go on with the damper, and b1 will be coming with the d by dt of, as we are considering the mass m1, so d by dt of y1 minus y2 will go. And these, so now I can see that there are three forces acting in the reverse direction from the applied force. So applied force is considered as input to this particular spring mass damper system, and the rest of the reaction forces are there. So this is the free body diagram for the mass m1, and then I'll have the free body diagram for mass m2. So I can just see that the input which is going to the mass m2 are the forces by the spring k1 and b1 damper. So the k1, now we are considering the mass m2, so y2 minus y1 will be contributed, and the force acting as input to the mass m2 by the damper is b1 d by dt of y2 minus y1 will go, and to these input to the mass m2 there will be reaction forces, and we know that there is the displacement y2 is there along with the mass m2. So the reaction forces on the mass m2 by the application of the sub forces from the k1 and b1, the reaction forces will be your k2. There is no further attachment, or there is no further mass attached to after m2. Okay, so it's a dead end here in this case. So k2 y2 will go on as the reaction force, and from the damper side b2 uh, y2 dot I can write, which is the dy2 by dt. So that's the free body diagram for this part. Okay, so this is one free body diagram, this is another free body diagram, and by using both of these free body diagram I can write the differential equation. I can write the differential equation. So let me just skip it away, skip it up, and write the differential equation. So the first differential equation from the first free body diagram can be written as uh, summation of all the forces going in and reaction forces. So the force applied was the input to the that, and all the there are three reaction forces. So I can write it as f of t equals to m1 d square y1 by dt square plus b1 d by dt of y1 minus y2 plus k1 y1 minus y2. So that's the first differential equation. And okay, and the second differential equation by the second free body diagram I can write it as so uh, there are two reaction forces uh, in total, if I want to see. Okay, so this also m2. Okay, I forgot to write one reaction by the body itself, which is your m2 d square y2 by dt square, right? So these three will go in one direction and these two will come from upward direction. So I can write this particular differential equation uh, by using this particular free body diagram. It has m2 d square y2 by dt square plus b2 dy2 by dt plus b1 dy2 by dt minus b1 dy1 by dt plus k2 y2 plus k1 y2 minus k1 y1 equals to 0. So that's my another differential equation, and this is my first differential equation for this particular example. This is my second differential equation for this particular example. Now what I can do is I have to assume the variables, state variables for these particular two differential equations, and that's the crucial part. Okay. So as I know that the displacements here is y1. So I am assuming x1 as first displacement y1, and I am assuming x2 as second displacement y2. So these are the two initial state variables. Now, and third one is the change in displacement y1, which is dy1 by dt, and that would be my x3. And x4 I'll consider as uh, the differentiation, further differentiation of uh, dy1 uh, dy2. So that's dy2 by dt, and that's my x3 and x4. So now if I want to look at the double differentiation of y1 and y2, so that would become my x3 dot as d d square y1 and dt square, and x4 dot would be my d square y2 by dt square. So I have these different, state variables and their differentiations. So now what we'll do is we'll put all these values of x1, x2, x3, x4, and x3 dot and x4 dot into the equation number 1 and 2 here, which we have. And then we will rewrite both the equations. So let's do this with the equation number 1. And F here is the applied force. If you look at this particular mechanical system, here F is your applied force. So it is acting as the input to the whole mechanical system. So we will consider this as U, and rest of the state variables we have defined here. So we'll uh, carry on further with that. So we are rewriting the equation 1 in the form of u and x. So we are rewriting the equation 1 as x dot is equals to f of x comma u. So your first order differential equation as the function of state and input variables. So we have u equal to m1 x3 dot. X3 dot is nothing but your d square y1 dt square. And if you can see here, that's it is in the equation number 1, m1 d square y1 dt square. Then you have plus b1 d by dt of y1 minus y2. So that would reflect here in the equation, rewriting equation. So it's your u m1 x3 dot plus b1 x3 minus b1 x4 plus k1 x1 x1 minus k1 x2. So this is our equation 1, and we will do the little bit of reshuffling, and then we will have m1 x3 dot equals to minus of bx minus of b1 x3 plus b1 x4 minus k1 x1 plus k1 x2 plus u. So and finally x3 dot equals to minus of k1 m1 x1 plus we are just rearranging and beginning from the x1 x2 x3, so it would be easy to make the final matrix out of these equations. So it's x3 dot equals to minus of k1 by m1 x1 plus k1 by m1 x2. Next I would write the x3 term, which is b1 divided by m1 x3 then I have x3, sorry, and then I have b1 m1 x4 4 plus 1 by m1 u. So that's my input term there. And this I can write as equation number 3 for the example 2. And similarly, rewriting the equation, second equation. So that should be my m2 x4 dot plus b2 x4 plus b1 x4 4 minus b1 x3 plus k1 x2 plus k2 x2 minus k1 x1 equal to 0. That's an equal to sign. Let me rub this and properly rewrite it. So that's uh, rewriting the equation. So I'll just do a little bit of reshuffling here and write it as m2 x4 dot equal to minus of all of it x4 minus of b1 x4 plus b1 x3 minus k1 x2 minus k2 x2 x2 plus k1 x1, and then I can simplify it a little bit, then minus of b2 plus b1 b1 multiplied with x4, putting these two terms together, then I have b1 x3 minus k2, it's a bracket here. I'll just rewrite the whole thing. Uh, it would be minus of k2 plus k1 multiplied with x2 plus k1 x1, and finally writing it as x4 dot, which is equals to k1 divided by m2 x1 minus k1 plus k2 divided by m2 x2 plus b1 by m2 x3 x3 minus b1 plus b2 divided by m x4, and that goes as my equation number 4 for this example 2. Now I have both the equations, both the differential equations which are rewritten, and now I know that I have assumed the two state variables. So x1 dot and x2 dot is coming from those places. So I'll have x1 dot equal to x3 and x2 dot equal to x4. Okay, so I'll have these two remaining mm, remaining first order equations as because as we know that x1 is equals to y1, and if we differentiate it with respect to t, then we get it as dx1 by dt is equals to dy1 by dt. And if we say that this is x1 dot and d1 y by dt becomes my x3 in that case. So by this we can conclude that x1 dot is equals to x3, and for the state, this was for the state variable x1 is equals to y1, and similarly for the state variable x2 is equals to y2. I differentiated dx2 by dt, and that goes as dy2 by dt, which is equivalent to x4, right? So it becomes as x2 dot equals to x4. So one equation from here and one equation from here, and I can finally write the whole state space representation of this particular mechanical system as x1 dot equals to x3, x2 dot equals to x4, x3 dot equals to, from this equation I have x3 dot as this particular uh, equation number 3 and x4 dot equation number 4. I'm rewriting both of these equations here, and x3 dot equals to minus of k1 by m1 x1 plus k1 by m1 x2 and minus b1 by m1 x3 plus b1 by m1 x4 plus 1 by m1 u. So here I have one input term in the x3 dot equation. There is no input term in x1 dot equation and x2 dot equation. I'll final write x4 dot equation, and as we can observe in equation number 4, there is no input term in that too. So it's a I can see that it's only one input is there in the x3 dot equation. So x4 dot equation would be my k1 by m2 multiplied with x1 and k1 plus k2 divided by m2. I'm writing this from this equation number 4. It's just the repetition of the equation number 4, and so this would be further um, multiplied with x2 plus b1 by m2 x3 minus b1 plus b2 divided by m2 multiplied with x4, and that's my set of equations which will be considered as state space model. Okay, so further on, I can form, it's clear now that I can form a state vector from here. I can write the state matrix A from by using these four equations. Okay, so that would be my initial. Most of the terms will be zero except uh, x3 vector and x4 vector. So these would be zero, and this is my initial two rows. Here is my x1, x2, x3, and x4. Okay, and my input matrix is having only 1 by m1 in third row, as x3 dot is having that 1 by m1 term, and then 0, and this is u. And I can write it as x1 dot, x2 dot, x3, and x4 dot. So that's my initial state vector. And these term would be my minus k1 by m1 and k1 by m1 again, minus b1 by m1 and b1 by m1 here in the third row, and fourth row would have K1 by M2, and second element of the fourth row would be K1 plus K2 multiplied by M2, and that's the water supply sound at my place. Please ignore it. And then we'll go by P1 by M2, and the final term as B1 plus B2 divided by M2. So that's my state space model for the mechanical system, which is shown here. This this is, and as far as I know, that the output is the displacement, and output is y1 and y2. These are my two uh, output equations, right? So so the displacement becomes the output of this particular mechanical system, and I can write the output as y1 is equals to x1 and y2 equals to x2. So the output equation in the matrix form can be written as y1 y2 equal to 1 1 0 0 0 0 0 0. All the elements would be 0, and we have the state vector as we have four state variables. That's why four state vectors. So that becomes my output equation, and the this one becomes my state equation, and this is our state space representation of the model which we have given. So this lecture here sums up the introduction of state space variables and the representation of an electrical system and a mechanical system uh, by using the state space approach. So this is here the introduction of state space analysis in this lecture. Thank you all for attending this class. That's it from the state space analysis. Thank you.